Thank you, and thank you for having me here again. So for this talk, I'm going to present mostly the work of my colleague, Matt Connolly, looking at using high-energy X-ray scattering to look at several different features in fatigue cracks grown in hydrogen that allow us to explore the effects of different hydrogen embrittlement mechanisms. So as a tendency, we tend to sort of look at results in hydrogen from a couple of different camps, and we're all guilty of this, including myself. And so if we look at from case of looking at mechanical testing, something like a tensile test, we go, oh, okay, we got this performance in air, we add hydrogen, we lose the ductility, so clearly there's a reduction in the plastic deformation with the addition of hydrogen. If we look at it more from, say, a microscopy point of view, then we look, okay, we have this is the failure in air, we have some ductility. In hydrogen, we have evidence of even more tight ductility right by the fracture surface. So maybe it's a manifestation in the plastic deformation that's changing when we deform in hydrogen. But then what happens when we look at something like fatigue crack growth rate? How do we pull out what's the plastic deformation contribution? How do we just... So are we looking at a change in the amount of deformation, the manifestation? Something we want to look at. And this camp tends to also deal with what mechanisms we tend to be attracted to. With the Heed mechanism, we look at hydrogen affects metallic bonding, so then we don't need to have a lot of ductility, so we can see hydrogen suppresses deformation. Or you look at it from the HELP mechanism or the nanovoid coalescence. With the HELP, you've got hydrogen affects dislocation motion, so that's a change in the manifestation of the plastic deformation. Or you have, more voids being nucleated and coalescing. With the nanovoid mechanism, again, that's a change in the manifestation of the plastic deformation. So in the last 10 years or so, we started changing our viewpoint a little bit finally and going, okay, maybe these are working in conjunction. Maybe we have a bit more synergy going on, that they're interacting. And so we want to have ways to sort of look at all of these simultaneously, and one mechanism to do that is by using high energy X-ray scattering. So we do this at high energy X-ray beamlines, and so we want to go there, be able to do mechanical testing in a hydrogen environment there. So we had custom built this rather small chamber. It's made out of aluminum that's only about 3 millimeters thick. That allows it to be transparent to both X-rays and neutrons. So we can also use this at a neutron site, and allows us to load our specimens while in a hydrogen environment right in front of the beamline. So for the data that I'm going to show here, my colleague Matt, he went to Argonne National Labs to use the advanced photon source there. The particular beamline is 1ID, and that's because of the particular setup there. So we have the beamline, we have our chamber that we can load the sample in, and then it has an array of 4 detectors such that we can get high angle diffraction, and then it also has a hole in the middle of this array such that we can get the small angle scattering as well. And we can do this complementary data at the same time through the same spots, and so we can load our sample in this chamber, and pause, and get all of that data. Oops, all right, sorry. It was rather slow to... Can you play the video for me, please? Just really quick, just so we have it. Yeah, right there, thank you. Yeah. So what we do in the facilities, we fatigue the specimen. We do it both in air and in hydrogen, and then we observe the crack length as it's by these X-ray radiographs, as you can see. And then when the crack progresses to certain points, we pause the fatiguing and hold it at the maximum load and do the mapping with the X-rays. And so for the first set of data, we can look at the strain mapping and convert that into stresses. And so here we have example stress map for in air and in hydrogen. You can look, here's the crack tip. You can see there's the stress there. It looks very similar until you start getting out to the far field. And so if we want to sort of start to quantify that difference, we have here the mapping of the log of the stress versus the log of the distance from the crack tip. And you can see in air, we've got this black curve here. We've got a large strain field right at the crack tip, which you'd expect. The J-dominant plastic region, again, you expect that. And then with the slope of -1/2, that's what you'd expect with the linear elastic region, the K-dominant region that allows us to do linear elastic fracture mechanics. If you look at the blue curve in hydrogen, though, we can see that at far field it starts getting different. We've got the large strain at the crack tip, J, and then we've got this linear elastic region, but then at far field, it comes out of this linear elastic region. So hydrogen's clearly modifying what's happening to give it so we don't have this as large of a linear elastic region. So to sort of show that in multiple conditions, I'm going to keep showing these sorts of maps. So here we have distance from the crack tip, where the crack tip's at 0, 0. So you have x and y. And in blue, we've colored in the region that's a linear elastic region to compare it for in air and in hydrogen. So we have in the top row, hydrogen taken at various crack lengths or k's, at the low, middle, and then very, very high. And we can see compared to an air, this linear elastic region is much, much smaller than the area in air until you get to the really, really high crack lengths where you're starting to get hinging and lots of plasticity effects in the samples. So clearly whatever hydrogen's doing here is somewhat similar to what's happening when you have lots and lots of plasticity towards the end of the crack. So let's look at what's happening with the plasticity. Let's look at the plastic zone size. And so we can get dislocation density from doing Williamson-Hall peak broadening analysis, and we basically assume just all of the peak broadening was due to dislocations to simplify the analysis. And that can give us a map of the dislocation density, and then we did a cutoff to give the dislocation, or to give the plastic zone size as a certain percentage of the dislocation density above the far field. And if we superimpose those areas on those previous maps, you can see the plastic zone size ahead of these linear elastic regions. And you can see certainly here, that's a much smaller plastic zone size than in air, similar here, until we get to the very, very large Ks, and then they start being similar. So this is not too surprising if you think of in terms of the help mechanism, where you've got effects on the dislocation interactions, you can pack them more tightly, so you can get a similar effect with a much, much smaller area. But if we want to do more than just compare blobs, let's actually quantitatively compare what's happening and look at the effect in hydrogen. We can see, okay, we're getting an increase in the plastic zone size with increasing K, but we've got this area in here from about 27 to 31 megapascal root meters, where there's this plateau where nothing happens, the plastic zone size doesn't grow. So what's going on here? Well, let's use our small angle X-ray and see if we can see what's going on there, and use that to do the plastic zone size. I forgot, since this is not my talk, there's one more bit in here. We wanted to see if this region compares to anything that's going on in mechanical testing. So this is the fatigue crack growth rate data. And what you can see is this plateau region starts right when you get an increase in the slope, and then it ends when you get this inflection point. It's subtle, but there's definitely an inflection point there. So there's something happening in the mechanical data that also corresponds to this plateau in the plastic zone size. And so we want to investigate that using the small angle X-rays. Now, I'm not a physicist. That's my partner, Matt Connolly, so I don't entirely understand the physics of what's going on here, but I'll tell you what we're looking for is we want to look in this region, which is the fractal region, and this corresponds to probing features of about the 2 nanometers to 100 nanometers scale size. And we want to look at the slope. That's the quantification that we want to look at. And at lower slopes, 1.6, that slope tends to correspond to signal given because all of the voids are about the same size in the distribution. You have this array. As you get a higher slope, 2.4, you get the surface fractal, where you have this distribution of void sizes. So you'd associate that with where you're starting to get coalescence of all these nanovoids into larger features. So we want to look at that, but we want to be able to sort of judge what we're looking at. So we did integrations over various areas. We looked at the far field to sort of get our baseline. We looked at the area at the cracked front, the crack tip, and then at the crack wake to see what's happening behind the crack. And you can see here's the typical data, and you can see while they're mostly close together, specifically to the far field, you can see the crack wake is a little bit higher, suggesting you've got a little more voids behind the crack tip, which is not surprising because that's all the damage behind where the crack has gone. So if we again look at the same K conditions in various cases in hydrogen and air, see, okay, in the first region, they're pretty similar. In this special region, in the middle, we can see there's actually this drop in the crack front ahead of the crack tip in these features, and that corresponds to what we see in air again at the large crack tips, or at the large crack lengths. So we're seeing again something similar that's happening in the special region hydrogen, what you'd see at far distances in air. So if we actually quantify that slope, what we can see is indeed we do get at that one point, the 27 megapascal root meters, the higher slope 2.4, which corresponds to this distribution of void sizes, suggesting that we are getting coalescence of these voids. And that's also what we see at the large crack tips in air. So similar thing is happening here. And then we have this region where it's higher but dropping. And then once again, we have the baseline for the rest of it, where we have this very, very normal distribution of void size is presumably small. Does this peak correspond to where we think it does? Yes, it does. This region where you have the plateau in the plastic zone size corresponds with this start peak, and then it decreases through the plateau region, and then enters again this baseline flatter area once we start growing the plastic zone size again. So if we're sort of looking at the region of where this is happening, we're integrating over about 2 millimeters ahead of the crack tip. And if we want to see what's going on, let's go back and look at what's the dislocation density as a function of region for the crack tip that's going through this area right here. And so you have the high dislocation density associated with the plastic zone. At the far field, you have this sort of flat distribution of the dislocation density. And then right in this region here, you have the slight depression, the slight decrease in dislocation density, right where we're getting these nanovoids coalescing. And so we think what's happening here is you're getting the help mechanism, you're getting more dislocation activity, and that's promoting the voids, and as the voids are coalescing, that's basically devouring the dislocations that are occurring. And so you're getting this interaction that's going on. So putting all of this data together, we suggest that there's 3 different regimes in the fatigue crack growth rate, and these all correspond to where different mechanisms are acting. So in the early parts of the curve, you have heat and help going on. That's with the variations on the plastic zone size that's affecting the far field stress fields. And you're starting to get some nanovoid coalescence from that activity. Then you enter into this plateau region where you're getting the help interacting with nanovoid coalescence, where nanovoid coalescence is becoming a major part of what's going on. And then that area starts dropping off again, and you go back to basically just heat and help happening. So in conclusions, we use both wide angle and small angle X-rays. We're able to probe multiple mechanisms looking at the heat, help, and nanovoid coalescence effects on the material. We were able to see that all of those were interacting in different ways, and an interesting result being that this nanovoid coalescence was only observed for this really narrow range in the fatigue crack growth rate. So this might explain some of the other results where people doing different microscopy and analysis techniques were picking up these nanovoids, but then in tensile tests and fatigue and fracture toughness, you don't necessarily see a big effect from the nanovoids. It could be because it's just not in the right K region to see that. And so I think there's a lot that we can get out of here. There's still a lot more analysis we want to do to make a complete picture, but I think it's very, very promising. And with that, I'd like to stop. Thank you for your attention and see if there's any questions.